Usually when we think about the act of forgetting, we think of it as a passive fading away.
Right, like it's just gone.
Yeah, exactly. Like a photograph slowly losing its color in the sun, or a thought that just sort of slips out of your grasp.
From a psychological perspective, I mean, we experience it as a lack of something.
It feels weightless.
A void where information
Oh.
used to reside, yeah.
But what if forgetting isn't weightless at all? Like, what if the simple act of discarding a bad idea actually physically heated up the room you are sitting in right now?
I know it sounds counterintuitive, almost like magic, really, but it is a hard, observable law of physics.
Wait, really?
Yeah. Information is not a ghost. It is a physical entity embedded in physical systems.
Okay.
And erasing it comes with a mandatory, unavoidable thermodynamic tax.
So every time you wipe a slate clean, the universe demands a payment in heat.
Exactly. You literally pay a heat tax.
Okay, let's unpack this. Yeah. Because we are going to take you on a journey today that weaves together three incredibly complex domains.
It's quite the overlap, yeah.
We are looking at the specific mechanics of a 2026 artificial intelligence competition called Orbit Wars. Then we're going to dig deep into the math of an AI decision-making architecture.
Monte Carlo tree search, specifically.
Right, MCTS. And finally, we're going to connect all of that to the mind-bending physics of Landauer's principle.
The goal here is to really show you how the spatial geometry of a seemingly simple video game dictates the causal logic of an AI trying to solve it.
And then how that AI's decision-making process, its constant generation and destruction of alternate futures, is ultimately bound by the thermodynamic limits of the universe.
It's a pluriversal synthesis of game theory, computer science, and hard physics.
So let's start with the arena, Orbit Wars. It's a programming competition hosted on Kaggle.
Which is a massive platform for data scientists, machine learning engineers, that whole crowd.
Right. And Orbit Wars is actually a heavily upgraded sort of spiritual successor to an older 2010 competition called Planet Wars.
But the developers fundamentally altered the physics of the game this time.
They completely shattered how an AI has to operate to win.
Yeah, the 2010 game was, at its core, just a graph.
Like a network map.
Exactly. If you think about basic network theory, you have nodes, which were the planets, and you had fixed edges, which were the travel paths between them.
So the AI just had to calculate the distance from node A to node B.
Right. It was discrete math. Simple, clean, highly predictable.
But Orbit Wars is completely different. It takes place in a continuous two-dimensional space.
The board is a 100 by 100 grid.
With the origin point coordinate 0, 0 up at the top left, and the entire map is laid out with a fourfold mirror symmetry.
Which is a crucial design choice, by the way.
How so?
Well, if there is a planet at coordinate 2525, there are perfectly mirrored planets in the other three quadrants of the map.
Oh, I see. It ensures a perfectly balanced start.
Right. No player has a geographical advantage based on where they spawn.
So you start on your home planet with 10 ships, and your opponents start on their mirrored planets with 10 ships.
But the center of the board is where the real problem lies.
Right at coordinate 50-50.
There is a massive sun.
A giant bonfire in the middle of the room.
Yeah, and it has a radius of exactly 10 units. And it's not just a background graphic, it is a lethal static hazard.
If you launch a fleet of ships, and their flight path intersects that sun's radius at any point,
those ships are instantly destroyed.
They just burn up.
Completely. So immediately, the AI cannot just draw a straight line from its current position to an enemy planet.
It has to route around this massive obstacle taking up the center of the board.
But it gets much harder because the targets themselves are moving.
Right, the planets are orbiting. Well, there are static planets sitting out on the distant edges of the map.
Yeah, but the inner planets, basically any planet where its orbital radius plus its physical radius is less than 50 units, are orbiting that central sun.
And we have to be precise about how they move.
We do. They travel along perfect circular orbits at a constant angular velocity.
And the parameters randomize every game, but it's typically between 0.025 and 0.05 radians per turn.
Which, for those of us who don't think in radians,
that means a planet is moving roughly 1.4 to 2.8 degrees along its orbital path every single turn.
So it takes anywhere from 125 to 250 turns for a planet to make one complete revolution around the sun.
Okay, got it. And the physical size of these planets isn't uniform either.
No, the game dynamically calculates the radius of a planet based on how many ships it produces per turn.
Wait, let me make sure I have this straight. So a high-value planet that produces, say, 5 ships a turn
is literally a larger physical object on the map than a low-value planet producing 1 ship a turn.
Oh, wow. So the more valuable it is, the fatter the target.
Yes, exactly. The exact mathematical formula is 1 plus the natural logarithm of its production value.
So a planet producing one ship has a radius of 1.
Because the log of 1 is 0, and a planet producing 5 ships has a radius of about 2.6.
And a massive planet producing 10 ships has a radius of roughly 3.3.
This means high-value targets are easier to hit physically, sure, but they are also easier for your enemies to hit.
And as if orbiting planets and a deadly sun weren't enough, the game periodically throws comets into the mix.
Ah, yes, the comets.
These spawn at specific intervals, right? Like turn 50, turn 150, turn 250.
And they fly through the board on highly elliptical trajectories. They basically act like temporary planets.
You can land on them, capture them, harvest the ships they produce.
But the catch is that they eventually leave the 100 by 100 grid.
Right. And when they do, any ships garrisoned on them just vanish forever.
It's an incredibly stressful logistical problem. You have to evaluate temporary assets continuously.
Capture the comet, hold it just long enough to reap the rewards, and then evacuate your fleets before it flies off into the void.
But the real nightmare, mathematically speaking, is how fleets move.
Let's get into that.
Yeah.
Because this is where the structural topology of the game completely breaks traditional pathfinding algorithms.
Yeah, fleet speed in Orbit Wars is not constant. It scales logarithmically based on the size of the fleet you launch.
So if I launch a single solitary ship, it moves at a baseline speed of 1.0 unit per turn.
But if you launch a massive armada of 1,000 ships, they don't move at 1.0 unit per turn.
They move much faster.
Right, they approach a maximum speed cap of 6.0 units per turn.
So a mid-sized fleet of, say, 500 ships would travel at roughly 5 units per turn.
Let's look at the spatial reasoning required here. In computer science, when dealing with continuous space, we often use something called RCC8 calculus.
RCC8, what does that stand for?
Region connection calculus. It's a formal system for defining the topological relationships between different regions in space.
So this is how the computer formally defines whether two objects are touching, overlapping, or completely separate.
Precisely. There are 8 basic relations. For instance, disconnected means the objects share no points.
Okay.
Externally connected means they are just touching at the boundary.
Like two billiard balls resting against each other.
Exactly. Then partial overlap means they intersect, and so on. In the old 2010 game, the AI didn't need this.
Because it just checked if a fleet arrived at a specific node.
Right. But in Orbit Wars, the AI must constantly evaluate the continuous spatial intersections over time.
Because it's not just checking if the final destination of the fleet overlaps with the center of a planet.
No, a fleet is a moving circle, the planet is a moving circle, and the sun is a static circle.
And the collision detection isn't jumping from point A to point B.
It actually sweeps the fleet's area across the entire line segment of its travel path for that specific turn.
So if that swept area achieves a partial overlap relation with the sun's radius at any fraction of the turn,
The fleet is destroyed.
and if it overlaps with a planet,
Combat triggers.
which means if an AI wants to attack an orbiting planet, it cannot just look at the board, see the planet at coordinate 4060, and aim there.
Because by the time the fleet arrives, the planet will have moved further along its circular orbit.
The fleet would just fly out into deep space and miss completely.
Right. The AI has to calculate an orbit intercept. It must solve for the exact launch angle. Let's call it theta.
Okay, theta.
But theta is dependent on the planet's initial phase, its constant angular velocity, we'll call that omega, and the fleet's variable speed, v.
But wait, the fleet speed changes depending on how many ships the AI decides to send.
Exactly.
So the AI can't even calculate the intercept angle until it decides the exact size of the fleet it wants to commit.
Which creates a massive recursive problem.
Because the size of the fleet determines the speed.
The speed determines the intercept point.
The intercept point determines how far away the planet will be.
And how far away the planet will be determines how many ships the enemy might have produced by the time you arrive.
Which changes how many ships you need to send in the first place.
It is a staggering level of complexity.
Yeah, it means the AI can't look at this 2D board in 2 dimensions. X and Y coordinates are completely insufficient.
It requires what we call z-axis inference.
Meaning?
In this context, time is the z-axis. The AI has to extrude the 2D board into a 3D volume.
Oh, wow.
When it looks at an orbiting planet, it doesn't see a circle. It sees a spiraling cylinder stretching upward through the z-axis of time.
And when it looks at the sun, it sees a massive static pillar.
And when it launches a fleet, it isn't drawing a line. It is projecting a cone of future trajectories.
So basically, you're trying to shoot a clay pigeon that's riding a merry-go-round.
Right.
But your bullet's speed changes depending on how heavy it is.
Yep.
And you have to curve your shot around a giant, unmoving pillar of fire in the center of the room.
And you have to do this simultaneously for every planet, balancing the math for every possible fleet size.
While your opponents are doing the exact same thing to you.
That is exactly the spatial bind the AI finds itself in. And to make matters worse, we haven't even talked about the primary constraint of the Kaggle environment.
Oh, right. The timeout limit.
The server gives your AI bot exactly 1 second to decide its move.
1 second. Act timeout equals 1.
1 second. You have to process the state of the board, run all the RCC8 collision calculus, solve the quadratic equations for multiple orbit intercepts, anticipate the enemy's moves, and issue your commands.
All in 1,000 milliseconds.
It seems impossible.
Well, why not just train a massive neural network? Feed it millions of games and let a deep learning model just instantly pattern match the best move.
That's a great question, and honestly, it's a trap many developers fall into early on.
Why is it a trap?
The problem is the 1 second bottleneck. Deep neural networks, particularly large transformers or convolutional networks, are incredible at pattern recognition.
Sure.
But running a massive inference engine deep into a complex branching future is computationally heavy.
Like how heavy?
Evaluating a single board state through a large neural net might take tens of milliseconds.
Which doesn't sound like a lot.
Not for one move, no. But if you need to search thousands of possible future states to ensure your fleet doesn't fly into the sun 20 turns from now.
Oh, I see. You will blow past the 1 second limit almost instantly.
Precisely. So pure machine learning is too slow. You need something much faster, much closer to the middle.
You need highly optimized forward simulation. Pure Python and NumPy arrays, stripped of any overhead, crunching numbers at blistering speeds.
And when we look at the developer logs from the competition, we can see exactly how the solutions evolved to handle this. They categorize the bots into tiers.
Tiers 1 and 2 are the foundational bots. The logs lovingly refer to Tier 2 as the nearest planet sniper.
I love that name.
It operates on pure, greedy logic. It scans the board, finds the closest unknown planet, checks if its homeworld has enough ships to defeat the neutral garrison.
And if so, it sends exactly the required ships +1.
It's the most basic heuristic human beginners use, but it fails spectacularly in orbit wars.
Because it completely lacks that z-axis inference, it aims at the planet's current XY coordinate.
It doesn't calculate the orbit intercept, so its fleets constantly miss.
And worse, it completely ignores the central sun.
Right. If the closest planet happens to be on the other side of the origin point, it just draws a straight line and sends its entire armada right into the fire.
It is entirely reactive to the present, with zero comprehension of the future.
So developers naturally evolved to Tiers 3 and 4.
This is where they mathematically solved the physics.
They implemented the correct orbit intercept formulas. They programmed the AI to calculate the varying fleet speeds.
And they introduced logistical heuristics, specifically ROI, or return on investment.
So instead of just attacking what's closest, the AI starts weighing the value of a target.
Exactly. A planet that produces 5 ships a turn, but only requires 10 ships to conquer, is a fantastic investment.
But a planet that produces 1 ship a turn but requires 50 ships to conquer is a terrible investment.
T3 and T4 bots also introduced defensive buffers. They stop sending every single ship they own, realizing they need a garrison to protect their home planets from counterattacks.
The solid Tier 4 bot will easily crush the lower tiers. It will navigate the sun flawlessly, hit its targets, manage its economy.
But the sources say Tier 4 bots hit a hard ceiling on the leaderboard. They can't actually win the tournament.
Why not? If they solve the physics and they understand economics, what are they missing?
They are missing causal logic. A Tier 4 bot is essentially just a really complex flowchart.
Right.
It evaluates the current state of the board and applies a set of rules. But it doesn't plan.
It doesn't set traps.
Right. To beat a grandmaster, you have to realize that a highly defended enemy planet is going to rotate behind the sun in exactly 22 turns.
Oh, wow. So the sun creates a tactical shadow.
Exactly. When that planet rotates behind the sun, the enemy cannot send reinforcements to it without routing the long way around.
Which takes extra time.
A truly advanced AI will realize this, calculate that its own fleet will take 20 turns to arrive, and launch a massive attack right now.
So the fleet arrives perfectly in that window of vulnerability, captures the planet, and the enemy's delayed reinforcements are too late.
A flowchart can't do that. You can't hard code every possible tactical shadow and orbital alignment.
You have to actually simulate the future.
Which brings us to the Tier 5 and Tier 6 bots, the absolute apex predators of orbit wars.
And the engine driving them is Monte Carlo tree search, or MCTS.
MCTS is one of the most elegant algorithms in artificial intelligence.
It was the backbone of DeepMind's AlphaGo, right? Which famously defeated the human world champion in the game of Go.
Yes, and Go has more possible board configurations than there are atoms in the observable universe. You cannot brute force every combination.
So MCTS is a framework that allows an AI to smartly guess which futures are actually worth exploring and which ones should be ignored.
Let's walk through how this actually works because it's fascinating. MCTS operates in a continuous loop of 4 distinct steps.
Step 1 is selection.
Imagine a tree. The root of the tree is the current state of the game right now. The AI looks at the valid moves it can make: launch fleet A, launch fleet B, do nothing.
It has to select a path down this tree of possible futures.
But it doesn't just guess randomly. It balances 2 deeply conflicting desires: exploitation and exploration.
And it does this using a formula called UCT, which stands for Upper Confidence Bounds applied to trees.
The UCT formula is the beating heart of MCTS. It's an equation that assigns a score to every possible move.
Let's break down the math.
Okay, the left side of the equation represents exploitation. It is simply $2 divided by $9.
So $2 is the number of simulated wins that a particular move has generated in the past.
And $9 is the total number of times that specific move has been simulated.
Because it's just the win rate. If move A was simulated 100 times and led to a win 90 times, its exploitation score is 0.9.
The AI looks at that and says, hey, this move usually wins. I should select it again and exploit that advantage.
But if the AI only ever exploits known good moves, it gets stuck in a local optimum.
It might find a pretty good move early on and never discover the perfect move sitting right next to it, simply because it never bothered to look.
It's the classic restaurant dilemma. You go to a restaurant, you order a dish, and it's fantastic.
Right.
The next time you go, you want to order it again because you know it's good. That's exploitation.
But if you do that forever, you never explore the rest of the menu.
Exactly. And you might miss out on a dish that is 10 times better.
So to force the AI to read the rest of the menu, the UCT formula has a right side, which represents exploration.
What's the math on that side?
The math here is a constant, etzebeller, multiplied by the square root of the natural log of capital $9 divided by lowercase $9.
Let's translate that into English for everyone.
Fair enough. Capital $9 is the total number of simulations run by the parent node, basically, the total number of times we've looked at this entire board state.
Okay.
Lowercase $9 is how many times we've simulated this specific move.
Okay, I see the mechanics. As the AI runs more and more simulations overall, the capital $9 gets bigger and bigger.
So the numerator of that fraction grows.
But if the AI keeps ignoring a specific move to play its favorite, that move's lowercase $9 stays small.
Yes. And mathematically, a growing numerator divided by a stagnant denominator means the value of that entire exploration term explodes.
The score just climbs higher and higher.
Eventually, the mathematical pressure of the unknown becomes so massive that it overrides the high win rate of the exploited move.
The AI is essentially mathematically compelled to say, okay, I've ignored this path for too long. I have to see what happens down here.
It actively forces the system to maintain curiosity.
That is brilliant. So the AI uses UCT to navigate down the tree until it finds a node, a future state that it hasn't fully evaluated.
That leads to step 2, expansion.
Which is pretty straightforward. The AI generates a new child node.
It formally adds a new hypothetical reality to the tree of possibilities.
And from there, we hit step 3, simulation, which is also called a rollout.
In a traditional vanilla Monte Carlo tree search, the simulation step is remarkably primitive. From this newly expanded node, the AI just fast-forwards the game to the very end.
It plays moves for both players completely at random until someone wins or until the 500-turn game limit is reached. Wait, random. Like it just matches buttons to see what happens?
In basic MCTS, yeah, pretty much.
And then step 4 is backpropagation. The random game ends. The AI looks at the result.
If the random simulation resulted in a win, it takes a 1. If it resulted in a loss, it takes a 0.
It takes that result and propagates it all the way back up the tree to the root.
Updating the win rates, those $20 values, for every move that led to that future.
And it does this loop selection, expansion, simulation, backpropagation thousands of times, building out this massive statistical map of the future.
Right.
But hold on. I'm seeing a massive contradiction here.
Let's view it through a pair-consistent lens,
Hmm.
a framework that looks at contradictions not as dead ends, but as opportunities to restructure the problem. What is the contradiction you see?
The timeout limit. The server gives the AI exactly 1 second.
Yes.
If an AI uses vanilla MCTS, it is taking a complex game state with rotating planets, logarithmic fleet speeds, and continuous spatial collisions, and it is randomly simulating 500 turns of that over and over again.
Great.
Random moves in orbit wars mean fleets flying into the sun, fleets completely missing planets, fleets just sitting there doing nothing. The AI is going to spend its entire 1 second budget simulating absolute garbage.
You've hit the exact bottleneck. The contradiction is this. To win, the AI must look deep into the causal future.
But to simulate deep into the future guarantees that it will run out of time and fail to act in the present.
Exactly.
So how do the grandmasters resolve this? How do you simulate the future without wasting the 1 second you have?
By using something called warm starting the MCTS and injecting combinatorial optimization.
What does that mean in practice?
Instead of running completely random simulations in step 3, the developers use their Tier 4 rule-based bots as the rollout policy.
Oh, that is incredibly clever.
Right.
So instead of simulating 2 drunk monkeys mashing the keyboard, you have 2 highly competent, perfectly rational Tier 4 agents play out the future against each other.
Precisely. You take the ROI calculus, the orbit intercept math, the defensive buffers that you perfected in Tier 4, and you let that logic drive the 500-turn simulation.
Because the Tier 4 bot uses fast, hard-coded rules, it executes instantly.
And more importantly, the simulation is profoundly realistic.
Because it's only simulating plausible futures. It's not simulating a future where a player intentionally flies 1,000 ships into the sun, because a Tier 4 bot would never do that.
Exactly. It drastically narrows the search tree, it prunes away billions of absurd realities, and forces the MCTS to only evaluate the tiny fraction of futures that might actually occur between 2 intelligent opponents.
And the sources mentioned they optimize this even further, using something called CMAES. What is that?
CMAES stands for Covariance Matrix Adaptation Evolution Strategy.
That is quite a mouthful.
It is. It's an algorithm used to optimize complex, non-linear problems. In this context, the developers use it to tune the weights of their Tier 4 heuristics.
Give me an example.
Okay, so how much importance should the bot place on a planet's production versus its distance? Is a high-production planet worth traveling 30 extra units for?
I see.
CMAES automatically evolves these variables over thousands of test games, finding the absolute perfect mathematical balance.
So the MCTS is being guided by an evolutionary algorithm that has perfectly tuned the heuristics of the simulation. That is terrifyingly efficient.
It allows the Tier 5 and 6 bots to run hundreds, sometimes thousands, of highly optimized, highly realistic 500-turn simulations within that strict 1 second window.
Okay, here is where my mind starts to bend. Let's look at the physical reality of what this computer is doing.
Let's do.
The AI runs 500 highly optimized alternate universes. It builds this massive tree in its RAM. It looks at the win rates. It selects the single best move for the current turn. It issues the command, and the turn ends.
Correct.
What happens to the data for the other 499 simulated futures?
The ones it didn't pick?
Yeah. The branches of the tree that didn't get selected, the universes that didn't happen, do they just vanish into the digital ether?
They don't just vanish. Data is not abstract. And this is the pivot point where we leave the realm of computer science and crash headfirst into fundamental thermodynamics.
Here we go.
Erasing those discarded futures requires paying a fundamental toll to the universe itself.
Let's talk about Rolf Landauer. 1961, IBM research. What was going on there?
In the early 1960s, computers were massive, room-sized behemoths, and they generated a tremendous amount of heat.
Right, vacuum tubes, early transistors, they were incredibly inefficient.
The engineers of the time knew that physical resistance in the wires caused this heat. But Landauer, who was a brilliant theoretical physicist, asked a much deeper question.
He wasn't asking about wire resistance.
No. He asked, is there a theoretical rock-bottom minimum amount of energy required to compute, even if you had a mathematically perfect, zero-resistance, frictionless computer?
Is heat a bug in the hardware, or is it a feature of the universe?
And his answer was Landauer's principle, which proved that, yes, there is an inescapable minimum energy cost, but it doesn't come from calculating.
It comes from forgetting.
Exactly. It comes from erasing information.
Landauer proved that erasing one bit of information dissipates a minimum amount of heat equal to kiloballers times the natural log of 2.
Let's break that equation down. Kiloballers is the Boltzmann constant.
Yes, named after Ludwig Boltzmann. It's a fundamental physical constant that relates the average kinetic energy of particles in a gas to the macroscopic temperature of that gas.
And kilodollars is the absolute temperature of the surrounding environment, measured in Kelvin.
Right, so kiloballer BT ln 2 At standard room temperature, this equation equals roughly 2.9 times 10 to the negative 21 joules.
That is an infinitesimally small amount of energy. It's almost nothing.
But the magnitude isn't what matters, right?
Right. What matters is that it is strictly greater than zero. Landauer proved that there is a hard physical cost to erasing information.
But to truly understand the mechanism, like how deleting a digital file makes a physical processor heat up,
Right.
we have to distinguish between logical irreversibility and physical irreversibility.
Let's use a tangible example. Let's look at a basic logic gate inside a computer processor, an AND gate.
Perfect. An AND gate has 2 input wires and 1 output wire.
Let's call the inputs A and B. Both can hold either a 1 or a 0. The defining rule of an AND is that it only sends a 1 the output wire if both input A and input B are 1.
So if A is 1 and B is 0, the output is 0.
Yeah.
If A is 0 and B is 1, the output is 0. And if both are 0, the output is 0.
Now imagine I put a black box over the input wire, so you can only see the output wire.
Nice.
I run the machine, and I show you that the output wire is currently a 0. Can you tell me with absolute certainty what the specific states of input A and input B were?
No, I can't. Because there are 3 different historical combinations that lead to that exact same result. It could have been 1, 0, 0, 1, or 0, 0.
The history of the system is obscured.
You cannot reverse engineer the inputs from the output.
The operation is logically irreversible. Information about the past state of the system has literally been lost. It has been erased.
Okay, I understand the logical part, but how does that create physical heat?
To understand that, we have to look at how physicists view information. In physics, a physical system is described by its phase space.
Phase space.
Yeah, it's a multi-dimensional map of all possible microstates the system could be in. When that AND gate takes 2 bits of input, which have 4 possible distinct states,
Right.
and compresses them into 1 bit of output, which only has 2 possible states, it is physically mapping many physical states onto fewer physical states.
It's physically shrinking the phase space.
Yes. And here is the unyielding wall of physics. The second law of thermodynamics. It states that the entropy, the total disorder or number of available microstates of an isolated system, can never decrease.
So if the computer memory compresses its phase space, it is locally lowering its entropy. It is becoming more ordered.
But the second law says that's illegal unless the entropy increases somewhere else.
Exactly. That lost entropy must be expelled from the memory device and dumped into the surrounding environment.
And the physical manifestation of expelled entropy is heat. Erasing information physically forces heat out of the system and into the room.
This connects beautifully to a very famous thought experiment in physics, doesn't it? Maxwell's demon.
Yes. James Clerk Maxwell proposed this in 1867. He imagined a microscopic demon guarding a tiny door between 2 boxes of gas.
The demon watches the gas molecules bouncing around.
When a fast-moving hot molecule approaches the door from the left, the demon opens it and lets it pass to the right.
When a slow, cold molecule approaches from the right, the demon lets it pass to the left.
Over time, the demon sorts the gas. All the hot molecules end up on the right and all the cold ones on the left. The demon has created a massive temperature difference out of completely random uniform gas.
Which is a direct violation of the second law of thermodynamics. You can use that temperature difference to run an engine and get free work out of it.
For decades, physicists were terrified by this idea because it suggested the second law could be broken.
But it was Leo Szilard and later Rolf Landauer who finally exorcised the demon. How did they solve it?
Szilard realized in 1929 that the demon cannot be omniscient. To sort the molecules, the demon must measure their speed, and it must remember that measurement.
The demon's brain, or its ledger, acts as a physical memory device.
And as the demon sorts millions of molecules, its memory fills up.
Exactly. Eventually, the demon has to erase its memory to make room for new measurements so it can continue the cycle.
And thanks to Landauer's principle, we know that the act of erasing that memory generates heat.
So the entropy decrease achieved by sorting the gas is perfectly canceled out by the entropy increase generated when the demon wipes its hard drives. The second law survives.
The second law always survives. But for a long time, Landauer's principle was just a theoretical argument. It took until 2012 for it to be definitively proven in a laboratory.
The Beirut experiment. This is fascinating. They didn't use a silicon chip or a normal computer. How did they prove this?
Antoine Beirut and his team used a single microscopic silica bead suspended in water. They used a highly focused laser beam, essentially an optical tweezer, to create a double well potential.
Imagine a tiny, invisible landscape with two distinct valleys separated by a hill in the middle. The silica bead is trapped in this landscape.
So if the bead settles in the left valley, it represents a 0. If it settles in the right valley, it represents a 1.
They built a 1-bit computer out of a floating microscopic rock.
Yes. To prove Landauer right, they had to erase this 1-bit memory, meaning regardless of whether the bead was in the left valley or the right valley, they had to force it into the right valley, a reset to 1.
And how do you force a microscopic bead into a specific valley without checking where it is first?
By physically altering the landscape. They slowly lowered the height of the hill separating the two valleys and gently tilted the entire laser trap to the right.
Gravity, or in this case the optical force, causes the bead to roll down into the right valley no matter where it started. Then they raise the hill back up and level the trap.
So they physically compressed the phase space. The bead had 2 possible states, and they squeezed the environment until it only had 1 possible state.
And as they did this, they measured the kinetic energy of the water molecules surrounding the bead.
When they forced the bead into a single state, the friction of that compression caused the bead to transfer energy into the water.
And the amount of heat it dumped into the water perfectly matched TQLB TLN 22.
That is incredible. It proves that this isn't just an abstract quirk of silicon processors. It is a fundamental property of the universe.
Regardless of the material, whether it is a laser trap, a vacuum tube, a modern microchip, or biological tissue, if you logically erase information, you generate physical heat.
Which brings us back to our Orbit Wars AI.
The Kaggle running its Monte Carlo tree search.
It uses its 1-second time budget. It builds a sprawling tree of 500 distinct alternate universes.
It calculates all the RCC-8 spatial collisions, the multi-way combat resolutions, the recursive intercept angles.
It finds the single path that yields the highest win rate, and it issues the command.
And then the 1-second turn ends. And the RAM, holding the data for the 499 universes that didn't get chosen, must be cleared to make room for the next turn.
The bits must be reset. Millions of logical states are compressed and merged into a state of 0. The memory is wiped.
And as those discarded futures are deleted, the silicon processor sitting in the Kaggle server rack is physically forced by the universe to dump heat into the room.
The computer physically warms up because it is actively destroying alternate realities.
Let that sink in.
That means if a bot is poorly programmed, say a tier 1 bot that just guesses random numbers and simulates absolute garbage futures where fleets fly into the sun over and over.
It's doing more than just wasting time. It's generating thermodynamic waste.
That is the concept of zero information simulations. A bad AI generates massive amounts of data that contains 0 strategic value.
It simulates nonsense, learns nothing, erases it, and does it again.
From a thermodynamic perspective, it is a purely dissipative system. The server running that AI is functioning as a very expensive space heater.
It is converting electrical power into heat without extracting any useful causal logic.
But a top-tier bot, a tier 6 bot, using CMA-ES to tune its heuristics, operates entirely differently. It isn't thrashing around randomly.
Right. It extracts what researchers call strategic knowledge.
It learns the deep structural invariance of orbit wars. It learns the mechanics of the tactical shadow behind the sun.
It learns how to use a moving planet as a sweeping shield against incoming fleets.
By utilizing that strategic knowledge to guide its Monte Carlo search, it avoids exploring the useless branches entirely.
It prunes the tree before it even grows.
It doesn't need to simulate 5,000 random futures. It only needs to simulate 50 highly plausible, incredibly targeted futures to find the winning move.
And therefore, the good strategy literally reduces the thermodynamic footprint of the computation.
By narrowing the search tree, you massively reduce the amount of information that must be generated and subsequently erased.
You compress the phase space with deliberate intention, rather than randomly thrashing around inside it.
Are there ways around this heat tax? I mean, computer engineers must be trying to build machines that don't generate heat when they compute.
There are theoretical models. One concept is reversible computing.
Okay.
If Landauer's principle says heat is generated when multiple inputs map to a single output, like an A and D gate, What if we build logic gates, where every input maps to a unique output?
Like a Fredkin gate, where you have 3 inputs and 3 outputs, and you can always perfectly reverse engineer the inputs from the outputs.
Exactly. In a perfectly reversible computer, no information is ever logically erased. The phase space is never compressed.
Therefore, in theory, it could compute without generating any minimum heat.
The problem is that to finish the computation and use the result, you eventually have to reset the machine, which brings the heat tax right back.
You just delay the payment.
Another fascinating approach is Langevin computers. Instead of fighting the thermodynamic noise, these theoretical computers actually use the random thermal fluctuations.
The Brownian motion of particles.
Exactly, to drive the computation forward toward equilibrium. They surf the heat instead of fighting it. But these are highly experimental.
For our Kaggle running on standard silicon, the heat tax is absolute. And this completely reframes the entire competition for me.
How so?
Think about the 1-second timeout. Act timeout 1. In a video game context, we view that as a software rule.
An arbitrary constraint imposed by the server administrators to make sure the tournament runs on schedule.
But if computation literally requires energy, and erasing bad computations physically dissipates heat into the universe,
then the 1-second timeout is not just an arbitrary software rule, it is a fundamental proxy for the energy limits of reality.
yes. The winning bot isn't just the one written with the cleanest Python code or the one that loops through arrays the fastest.
The winner of Orbit Wars is the entity that transforms raw data into strategic insight with the absolute minimum amount of wasted phase space exploration.
That is an incredible synthesis.
Yeah.
The Kaggle leaderboard is, in a very real physical sense, a ranking of thermodynamic efficiency.
The agents sitting at rank 1 are the ones that extract maximum causal logic while generating the minimum possible entropy.
The winner is the one who wastes the least amount of physical reality to secure a victory.
We have covered a massive amount of ground today. We started by mapping out the spatial topology of a 100 by 100 continuous grid.
We looked at how an AI must use RCC8 calculus to dodge a static sun while solving quadratic equations to intercept rotating targets.
We looked at the necessity of z-axis inference treating time as a physical dimension to project a 3D cone of future spatial intersections.
From there, we broke down the cognitive architecture of Monte Carlo tree search. We examined the UCT formula,
Dissecting exactly how the mathematical tension between exploitation and exploration forces an AI to maintain curiosity.
and we saw how injecting rule-based heuristics into the rollout phase solves the pair-consistent contradiction of needing deep foresight but having no time to acquire it.
And finally, we grounded all of those digital mechanics in the bedrock of physical law. We traced the history from Maxwell's demon to Szilard to Landauer.
And finally, to the Beirut optical tweezer experiment.
We proved that information is physical, and that erasing a digital universe from a silicon chip comes with a mandatory toll of kB/ln 22 joules of heat.
It changes how you perceive computation. A computer isn't just an abstract math machine.
It is an engine that molds physical reality, generating universes of possibility and destroying them.
Paying a heat tax for every single discarded timeline.
It's profound. It takes something as dry as an AI competition and turns it into a microcosm of the laws of thermodynamics.
And it leaves us with an important question to consider, one that stretches far beyond silicon processors and Kaggle leaderboards.
What's that?
If Landauer's principle applies to all physical substrates that process information, whether it's a microscopic glass bead in a laser trap, or a vacuum tube, or a modern transistor.
What does that mean for the human brain?
Exactly. The brain is a physical substrate.
Oh, wow. It is entirely physical. It obeys the exact same laws of thermodynamics.
Think about the sheer volume of microsimulations you run in your head every single day. The anxieties.
The branching paths of, what if I said this to my boss, or what if I took that route to work instead?
You simulate thousands of alternate futures, evaluate their outcomes, and discard the vast majority of them.
You are constantly expanding and pruning your own internal Monte Carlo tree search.
And every time you discard one of those imagined futures, your biological neural network has to erase that information. It has to compress its phase space.
Which means there is a physical thermodynamic cost to human intuition.
Exactly. How much literal physical heat does it take for you to change your mind?
When you are obsessing over a decision, running redundant, zero-information simulations in your head, you are just wasting time.
You are functioning as a dissipative system.
The friction of cramming thousands of imagined alternate realities into the single box of the present moment, It literally generates heat.
Burning calories by overthinking isn't just a metaphor, it's thermodynamics.
The physics of forgetting is happening inside you right now with every passing thought.
I am going to be turning that over in my head and probably generating a little heat while doing it for a long time.
Thank you so much for joining us on this deep dive into the geometry of orbit wars, the mechanics of AI foresight, and the inescapable thermodynamics of information. Keep exploring, and we'll see you next time.